Have you ever looked closely at something like a beautiful amethyst crystal and just wondered, what's going on inside? I mean, what if we could build a perfect digital copy of it? Not just a pretty picture, but a full-blown digital movie, simulating every single atom as it jitters and hums. Well, that's exactly what we're going to explore. Let's start this quest to build the perfect digital crystal.
So right off the bat, that is the huge question we're trying to answer. Is it actually possible to create this perfect digital twin of something real, right down to the last atom? It seems simple enough, but, the journey to find the answer, well, it uncovers some absolutely incredible truths about the very limits of what we can compute.
All right, every great quest needs a first step. And for us, that means we've got to pick the right tool for the job. We're going to need some serious computational horsepower, an engine that can handle gigantic numbers and do it super fast. So let's see how 4 different approaches fare in a head-to-head performance test.
Okay, so here are our first 2 contenders. And, well, they're surprisingly inefficient. The string engine literally treats numbers like they're words, which means it's always converting them back and forth. It is slow and it creates a ton of what we call digital garbage. We're talking over 300 cleanup events in our test alone. Then you have the object-oriented engine. It's a bit tidier, but creating a whole new object for every single number, that adds its own drag, making it pretty slow too.
But thankfully, there are much smarter ways to do this. Enter the big integer engine. Now this thing is specifically designed to handle absolutely massive numbers. Numbers so big you can barely write them down. And because of that, it's way faster than treating numbers like they're just pieces of text. And this chart, wow, this just says it all. The scientific number engine, which uses the computer's native super fast math abilities, just completely destroys the competition. I mean, look at that, over 2 billion operations per second. The others are barely breaking 1 million. It's not even a fair fight. So we've got our champion engine, we're ready to build our crystal now, right? Well, not quite so fast. You see, picking a fast engine was a great first step, but now we have to face the true scale of the problem we're trying to solve. And honestly, it is staggering. It's almost unbelievable. Just take a second and really look at that number. 10 sextillion. That's how many individual atoms are packed into a tiny piece of amethyst, just 1 cubic centimeter. That's a 1 with 22 zeros after it. This isn't just a big number, it's a number on an astronomical scale. And realizing this, well, it changes everything.
And here's the absolute heart of the problem. Our superfast engine, it's great at representing the number 10 to the power of 22. No problem. But that's not what a simulation does. A real simulation, that digital movie we want to make, has to track every single one of those 10 sextillion atoms as its own thing, calculating its position, its speed, and how it's interacting with all of its neighbors all at once.
And all of a sudden, our grand quest just slams into what feel like completely insurmountable obstacles. We're not just dealing with a big number anymore. We are now officially up against the fundamental, hard limits of computation itself.
You can think of these limits as 3 giant walls standing in our way. You've got the mathematical wall, the performance wall, and the architectural wall. And here's the kicker. Any single one of these would be enough to stop our project cold.
So first up, the mathematical wall. See, the complexity here doesn't just add up, it explodes exponentially. Every single one of our 10 sextillion atoms is interacting with a whole bunch of its neighbors. This creates a web of connections that is just unimaginable. To calculate just one tiny step forward in time for a simulation, like a single frame in our movie, we might need something like 10 to the 24th power calculations.
And that leads us straight into the performance wall. Let's take the Frontier supercomputer, one of the fastest machines on the entire planet. It can crank out about 10 to the 18th operations per second, which sounds amazing, right? But it's a tiny drop in the ocean compared to the 10 to the 24th calculations we need for just one step. Even our most powerful computers are just completely overwhelmed.
And finally, we smack right into the architectural wall. Okay, forget about speed for a second. Just where would you even store all the data for 10 sextillion atoms? The amount of memory you'd need is more than anything that currently exists on Earth. And even if you had it, just moving that data around to be processed would be an even bigger bottleneck. It's a physical hardware problem we can't get around.
So this really brings us back to our goal of making a beautiful movie. It's so important to understand the difference here. A visual rendering, that's basically an illusion. It's like a Hollywood special effect that uses clever tricks and shortcuts to make a pretty picture.
But a true physical simulation, that's a scientific model. It's calculating the real physical forces between every single atom. One is art, the other is a whole different level of science.
So, looking at these massive, unscalable walls, it's easy to feel a little bit defeated, right? Does this mean the whole quest, this idea of a perfect digital crystal, is just a pipe dream? Is it a complete failure before we even really get started?
No, absolutely not, because this is what scientists do. When they're faced with a problem that seems impossible, they don't just give up. They get clever. They figure out a smarter, more elegant way to get the answers they need without having to do the impossible. And that brilliant, clever solution is called multi-scale modeling. The idea is, instead of trying to simulate every single atom in a giant crystal, which we know is impossible, scientists simulate a very small, manageable chunk of it, maybe just a few thousand atoms. But they simulate that tiny piece in excruciating, perfect detail, learning everything they can about how those atoms interact.
It's really this beautiful three-step dance. First, you run that microsimulation to get these fundamental insights. Second, you take what you learned and you build mathematical rules or models that describe how the material behaves on a larger scale. And finally, you apply those simple, efficient rules to the whole crystal to predict its real-world properties, like its strength or how it grows, all without ever having to simulate those 10 sextillion atoms. It's genius.
And that right there, that's the core lesson of our entire quest. The biggest challenge in computational science, the real frontier, isn't just about handling big numbers. It's about figuring out how to manage the absolutely enormous number of individual particles and the mind-boggling complexity of all their interactions. It really makes you wonder, doesn't it? What other things in our world seem simple on the surface, but are actually hiding a universe of impossible complexity, just waiting for a clever mind to find a new way of looking at them?